Welcome to Amateur Radio's Reflector Magazine by the East Coast Reflector. Volume 25 of the Reflector Magazine, February 2026. Articles featured in this volume: Dick's Corner, The Antenna Farm, Terms and Magic, KC6UFM, a small HF antenna, SM0VPO. What is Whisper? VK3AWA. Basics, Frequency versus Band, KE8VKY. Celebrity Call Sign K1JT. Dr. Joe Taylor by KB2TFB. World Radio History, Radio Questions Answered. You'll also find information on nets, user-submitted pictures, Zoom events, system and connection information, silent keys, and more. Table of Contents. What's in this article, Dick's Corner? This issue brings together the latest updates, announcements, and milestones from around the East Coast Reflector. Here's a quick look at what you'll find inside. Date and details for the 4th Annual Western New York Meet and Greet. Team member updates. Announcement of the new ECR System Coordinator. A status update on the QSO Quest program. Results from the top 20 Morning Brew check-ins for 2025. Plenty of news, a few congratulations, and a look ahead at what's coming up across the ECR. Mark your calendars. Western New York Meet and Greet returns. The 4th Annual Western New York Meet and Greet is officially on the calendar. The event will take place on June 20th, 2026, once again at Chestnut Ridge Park, just south of Buffalo, New York. This popular yearly gathering is a great opportunity for hams to meet face-to-face, talk radio, and enjoy a relaxed day together. More details will be shared over the coming months, but now is a great time to mark the date and plan to attend. It's always a fun day, and we hope to see many of you there. ECR System Coordinator Announcement. Vicky KE8VKY has been appointed as the ECR System Coordinator. In this role, Vicky will serve as the primary point of contact for ECR activities, helping with coordination and communication across the system. Please join us in congratulating Vicky and wishing her continued success in this new position. The top 20 Morning Brew check-ins for 2025 have been tallied from a total of 251 Morning Brew sessions. Congratulations to everyone who made the list, and thank you to all who regularly check in and help keep Morning Brew active and lively. We're also excited to welcome 2 new voices to the Morning Brew lineup: Scott and 7FPG Bill, KF0MHN. Both are generously volunteering their time and talents to help guide the net each morning. Please join us in giving Scott and Bill a warm welcome and a big thank you for supporting Morning Brew. Open Mic Night Team Update. The East Coast Reflector is pleased to announce an expansion of the Open Mic Night Team. Joining Mark, KE2EDS, R. Terry, and 5RDC, Gil, K4GDS. Both bring years of experience and fresh ideas and will help keep Open Mic Night running smoothly and enjoyable for everyone involved. If you're interested in becoming a net controller, you're invited to fill out the form at ecr.radio/joinopenmic, and a team member will contact you. No commitment required. QSO Quest Update. QSO Quest is going to be an ongoing initiative designed to encourage increased on-air participation across the East Coast Reflector Network. Questers earn points by making QSOs with designated coasters and work toward earning certificates. Any mode may be used. Contacts are logged through a link on the ECR website, and points are awarded only for contacts made with stations designated by the ECR team. Coming soon. Dick, WB2JPQ. Meet your control stations. Sometimes people with good intentions act as control operators, but don't represent the ECR. This is the official list of active control stations. Bob, KB3SNM. Dick, WB2JPQ. Kevin, KE7K. Joe, KO4FRR. Kevin, VE3BZ. Vicky, KE8VKY. Charles, KC6UFM. Dan, KD2VNU. Backup control stations are also available. Connecting to ECR is simple, and there's no membership or club to join. Everyone is welcome. There are no fees or permissions. Just connect. If you have audio or connection issues, we're here to help. Simply free. The way that air was meant to be. Connecting to the ECR with the Shark RF via Echolink. The Reflector Magazine is available on YouTube. Watch along on the pages and listen to the voiceover as it reads to you. It's great for blind, visually impaired, people who'd prefer to listen to the audio, or people who need something to listen to while they mow the lawn. If you know of someone who would benefit, pass it along. The ECR can use your help. We need net controllers and loggers. We also need a Zoom greeter and a podcaster for YouTube. Reflector etiquette. Here's a list of common courtesies for the reflector.
In this article, antenna discussions are full of numbers, claims, and abbreviations that often sound impressive, but don't always mean what people think they do. In this look back into the antenna farm, Charles clears the fog around common antenna terms and exposes a few bits of marketing magic every ham should recognize. What is a decibel? How gain and loss work together? Why the half-wave dipole became the measuring stick for antenna gain? The difference between dBd and dBi and why it matters. What is an isotropic radiator? Why digital antennas aren't a real thing. How to spot misleading antenna specs before opening your wallet. This groundwork will make it much easier to evaluate antennas and feed lines as a complete system as we move forward in the series. The Antenna Farm. Part 2. Terms and Magic. Hello, ECR family, and welcome to the Antenna Farm. I'm your friendly antenna farmer, Charles, KC6UFM. While I try to make the articles in this series freestanding, so you need not read them all in sequence, a certain amount of information is needed for a total novice, no pun intended, to understand things fully. As a rule, that needed information is covered in earlier articles. So, while I make an effort at the freestanding of each article, odds are you'll get more out of the series if you read them in order. This time, we're going to look at a few common terms used in antenna work, and a few feats of magic you may see from time to time related to them. Terminology and the misunderstanding misuse thereof is very common in amateur radio. As you read this, try to think back on how you have seen these terms used and how some hams have presented them to you. Term number 1, decibel. There is a fairly simple equation to calculate decibels, usually abbreviated as dB. It's not too complex, but we're going to totally ignore it. Why? Because, simply put, it doesn't matter for our needs. What is important, however, is that you understand that a dB is a mathematical ratio. That is to say, it compares two values. A statement like, my antenna has 3 dB of gain, has a net meaning of absolutely nothing, because we don't know what things are being compared. You must know the basis of comparison, or the dB value is meaningless. By one of those coincidences that makes you believe in a supreme being, it just so happens that a change of 3 dB is very close to a factor of 2. In other words, if, let's say, you have an antenna with 3 dBd of gain and put 10 watts of power into the antenna, the apparent output from the antenna will look like 20 watts coming from a dipole. This is a radical simplification, but you'll learn what strict reality is soon. As a side note, when we talk about the loss in a feed line, coax, open wire, whatever, it is assumed that we are comparing the feed line loss to the loss of a perfect, lossless conductor. The whole world is waiting for room temperature superconductors, but I digress. Term number 2, gain/loss. First off, and I know I'm going to get flack for this, gain and loss are the exact same thing, just that one gain is given a positive value and the other loss is treated as a negative number. Other than the numeric sign, they are the same. And this is where our first bit of magic comes in. Gain and loss figures expressed in dB can simply be added together to get the total system value. That's right, no nasty calculations or slide rules or even calculators needed. Just plain old garden variety addition. Well, there is the addition of negative numbers, and we call that subtraction. As a very simple example, let's assume you have an antenna with 3 dBd gain and a feed line with 3 dB of loss. All you need to do is 3 plus minus 3 equals 0 dB, and you know that the system, antenna plus feed line, has a total of no gain or loss. Ain't math great? Term number 3, dipole. A theoretical dipole is nothing more than an antenna with 2 elements, poles, each being fed with one of the 2 feed line wires. That's all. Nothing about length or diameter or any other property. That said, a half-wave dipole, a dipole with a total electrical length of 1/2 wave of the operating frequency, is what most hams think of when talking about a dipole antenna. While the theoretical dipole is the simplest antenna, the one-half wave dipole is the simplest practical antenna. Because of this, a standard has emerged that uses the one-half wave dipole as a reference point. Almost all the reputable antenna makers out there will indicate their antenna products gain when compared to a dipole. This is abbreviated as dBd, standing for decibels over a dipole. In other words, if Comet says a particular antenna has a gain of 3 dBd, they are saying that their antenna will show an apparent power twice that of a half-wave dipole. Term number 4, isotropic radiator. An isotropic radiator, sometimes but rarely called an isotropic antenna, is a purely theoretical point source of a signal. Before you try it, you cannot build an isotropic radiator. It exists only in the universe of pure, esoteric mathematics. That doesn't mean that it isn't useful, but more often than not it is used to artificially inflate gain figures of antennas. How's that, you ask? Simple. A dipole, see above, has a gain of about 2.14 dBi. Note either, to rephrase this, the dipole has 14 dB gain over an isotropic radiator. So what? Less reputable antenna makers will often give their products gain figures in dBi instead of dBd. Some even leave off the third character altogether. Say you're shopping for an antenna. You see two similar antennas, and one claims to have 3 dB of gain, and the other claims 5.14 dB of gain. With what you now know, you should see the problem here. The first figure tells you explicitly that the antenna has 3 dB of gain over a dipole. The second does not give you the basis of comparison at all. 5.14 dB of gain over what? We don't know. Therefore, the value has no meaning at all. If the less than ethical manufacturer does add the trailing I to the figure, it's better. But in all honesty, most hams will not see the I, or even the D, and just assume the latter antenna has more gain when, in fact, they are identical. Warning. If an antenna add manual document does not clearly state if their gain figures are in dBd or dBi, you should pass them by. They are trying to scam you out of your money. The bottom line here is that if you are antenna shopping and you see one antenna rated in dBi, all you need to do is subtract 2.14 from that value to convert it to dBd. Now you'll be able to compare the antennas fairly on a level playing field. Magic digital antennas. This has been happening for several years in the world of OTA TV antennas, but I'm starting to see some ham antenna ads touting antennas for digital modes like DMR, YSF, etc. Popping up in magazines, yes, QSD and CQ, and online at both Amazon and eBay. The pitch is that to work digital modes or HD plus TV, you need a special antenna. This is, in short, nonsense. Antennas are specific to a given frequency or range, but not to mode, and DMR and the rest are just modes. Most hams use the same antenna for CW, SSB, AM, FM, FT8, SSDV. You get the idea. The antenna only cares about the operating frequency, not the mode. This advertising magic is a clear attempt by the manufacturers and retailers to take advantage of both the explosion in the digital modes and the influx of new hams who may not have the experience and knowledge needed to see when they're being scammed. Don't fall for this. You now have a few simple terms to help you understand how antennas are rated. As a bonus, the same terms apply to feed lines as well. This means that as we move forward together, you'll be able to look at the system as a whole and be able to evaluate potential performance. In our next visit, we're going to look at feed lines and then take a trip to the antenna farm to harvest a very simple, effective antenna for VHF-UHF operations that you can build with a few common hand tools and for well less than $10 in cash. Take care in 73. The KC6UFM. Charles. Other articles by Charles KC6UFM.
Connections. Connections printable. There are many ways to connect to ECR. For a printable list, go to ecr.radio/connect. There, you will find the information on the many different ways to connect. Got DMR? Connect to the East Coast Reflector using 3215714. You can find a map of repeaters on eastcoastreflector.com. If you have a repeater that's connected at least 60% of the time, is 10 watts or more, has an outside antenna, and is open for others to connect, then let us know and get on our map. The ECR is on Discord. Join us at ecr.radio/Discord. Social media. The ECR is building up its social media presence. Join our Facebook group so you can enjoy our ham radio content and stay up to date on ECR information, and so you can update us on your ham shack and ask questions. Just like on the air, we don't tolerate trolls. You're free to ask questions troll-free. We keep it an enjoyable place. Check us out also on X, Twitter, Groups.io, YouTube, and most recently Discord. We look forward to you joining us. What's in this article? What's in this article? Making HF antennas work in a tiny garden. Working HF from 3.5 to 29.7 MHz is straightforward until space, visibility rules, and a single coax run make it anything but. In this article, SM0VPO documents the experiments and design choices that led to an effective, low-profile HF antenna system for a very small garden. You'll find real-world constraints of operating HF from a restricted residential plot. Vertical versus horizontal antennas. What actually worked and why? Base-loaded, folded, and multi-band dipole experiments. Practical construction tips, formulas, and trimming techniques. A final stealthy, efficient antenna covering 7 MHz to 29.7 MHz with no ATU. This is a candid, experiment-driven journey from no space, no options, to a reliable multi-band HF antenna that stays on the air and out of sight. Introduction. Over the past 2 months, I have been playing with HF antennas in the range of 3.5 MHz to 29.7 MHz. My basic problem is one of the two radio amateurs' nightmares: lack of space. I just don't have it available. I used to live in a villa outside Orlando, and with 2,200 square meters of garden, I was spoiled rotten. Just for fun, I put up a full center-fed dipole for 1.8 MHz. Today, I have a little house in Marsta with a very small garden that is just 8 meters wide. In addition, I have a local community that have strict regulation as to what I can erect. Basically, if it has a high profile, then I have to take it down. I need to find a limited space antenna solution that will let me use 7 MHz through to 29.7 MHz. 3.5 MHz has been achieved, but I have an S9 level of noise on the 80-meter band, so that will be a project for later. My little plot of land behind hedge for antennas. I cannot have antennas on the communal grass area. In addition to this, I cannot run loads of wires beside the house as it is an in-terrace house. There is only one neighbor, smiley face, but the other side is visible to the public and the community officials, sad face. I can realistically get away with just one coaxial cable. So here are the results of my experiments and my final result that will cover all bands from 7 MHz to 29.7 MHz. I can also add 3.5 MHz, but I will just give you the information for that band and see if you get a better solution. Experiments. If you check my message board, SM0VPO forum is here. You will see some of my posts and some of the really valuable and clever ideas I received. I actually did try some of the ideas, and some I incorporated in the final design. Others were discounted for several reasons. I do have a lovely variable length antenna yet to experiment with. One experiment was to use computer ribbon cable. The conductors were all connected together to form one half of my dipole. The other ends were stripped back and cut to different lengths to get a resonance at the bands of interest. The last meter of each element was left hanging in an effort to stop interaction between elements. I did get a multi-band antenna working, but when running only 100 watts, the thin cable at the feed point got hot and even melted the plastic. I believe the thin conductors were dissipating more than a little RF power. It is a pity, as this would have been an elegant and low-profile solution. I regularly use Voice of Russia 7.205 MHz AM as a 40-meter test station. A good test at night for almost the 20-meter band is the BBC World Service on 12.095 MHz. Vertical or horizontal? I also experimented with vertical, ground plane, and horizontal dipole antennas. There are different reasons for choosing vertical or horizontal antennas. Vertical ground plane, 1/4 wavelength, Antennas are easy and do not require any antenna support structure other than some form of foot for it to stand on. Unfortunately, a 5-meter high vertical has a maximum radiation from about 2 meters off the ground. This is okay for use in the clear without any surrounding obstacles. In my restricted garden, I have bushes and garages obstructing the field of radiation. So I can use a vertical for mobile or portable use, but not at home. The height needed for any frequency is given by the formula. Height equals 71.25 meters divided by frequency in megahertz. Ground plane antenna with obstructions. Trees and bushes are not nearly as bad in nearby buildings. Continued on page 87. If you'd like to skip ahead now, there's a link in the description below. Join us Tuesday nights at 8 p.m. Eastern for the ECR Tech Net. The Trivia Net Saturday nights at 11 p.m. Be a net controller on our open mic net Wednesdays at 8 p.m. Register at ecr.radio/join open mic. Go to 14.317 Thursday mornings at 10 a.m. and 7.245 on Saturdays at 9 a.m. An infamous morning brew weekdays from 7 to 9 a.m.
What's in this article? Using WSPR for antenna testing. WSPR is often described as a propagation experiment, but many amateur radio operators use it as a powerful real-world tool for antenna evaluation. By transmitting standardized, low-power signals and analyzing worldwide reception reports, meaningful performance comparisons become possible. This article focuses on how WSPR can be used practically, not theoretically, to compare antennas and station setups using repeatable, on-air data. In this article, you'll learn what WSPR is and why it was created, how standardized low-power transmissions enable fair comparisons, why WSPR works well for HF antenna testing, how timing, power, and consistency affect results, what WSPR reports and maps really show, why trends matter more than individual spots, practical tips for using WSPR as an antenna evaluation tool. This introduction sets the stage for using WSPR effectively while avoiding common mistakes, helping operators get reliable, useful results from their experiments. What is WSPR? WSPR is an acronym for Weak Signal Propagation Reporter. It's a digital radio communication protocol developed by Joe Taylor, K1JT, a Nobel Prize-winning physicist and amateur radio operator. Purpose: WSPR is designed to probe and map radio wave propagation over long distances using very low power transmissions. It helps radio amateurs and researchers understand how radio signals travel around the world under different atmospheric conditions. It's actually one of the best practical tools for HF antenna testing, since it provides a standardized low-power signal that's automatically logged worldwide. By comparing how your signal is received with different antennas, you can build a clear picture of their relative performance. Here's a step-by-step overview on using WSPR to compare antenna performance. 1. Set up your WSPR station software. Install WSJTX or a dedicated WSPR program. In WSJTX, select WSPR as your mode of operation. Hardware. Use your HF rig setup for digital modes and set the power output between 1 to 10 watts. Also, dedicated low-cost WSPR transmitters are available from Zactec Computer Clock. Ensure your computer clock is synchronized, NTP or GPS. WSPR requires precise timing. 2. Choose antennas to compare. Make sure you can switch easily between antennas, manual switch or remote antenna switch. Test antennas that operate on the same frequency band. Example, 20-meter dipole versus vertical. 3. Run controlled tests. Pick a band and frequency. Example, 14.0956 MHz on 20 meters. Operate one antenna for a set time period. Example, 5 to 15 minutes. Switch to the other antenna using the same transmitter power and the same time period. Avoid making changes other than the antenna itself. Run comparisons at the same time of day to avoid propagation differences. 4. Check out results after each antenna session. You can use online WSPR mapping tools to compare your results. pskreporter.info, wspr.rocks, or WSPR Watch for iPad and iPhone users. 5. Compare results. If antenna A consistently gets more spots or higher SNR than antenna B, it's maybe more efficient. If antenna A reaches further DX, but antenna B gets stronger local reports, one has a lower takeoff angle, while the other favors NVIS, near vertical incidence skywave. Compare not just raw numbers, but the propagation footprint maps. Keep in mind WSPR is a statistical tool. You're looking for overall trends, not a single spot. Conclusion. This is just an introduction and overview of how you might use WSPR as a great tool for antenna testing and comparison. I use it all the time to evaluate new antennas that I build. I have a benchmark antenna as my reference standard. Have fun, 73, Daryl VK3AWA. Be a Quester. QSO Quest is going to be an ongoing initiative designed to encourage increased on-air participation across the East Coast Reflector network. Questers earn points by making QSOs with designated coasters and work toward earning certificates. Any mode may be used. Contacts are logged through a link on the ECR website, and points are awarded only for contacts made with stations designated by the ECR team. Coming soon. It takes many people to keep the system running. Audio check. There are great audio tools on the website at eastcoastreflector.com. There's a Listen Live player for listening anytime, equipped with a visual audio meter. There's a second player with a 2.5-minute delay. This allows you to do your own audio check. To hear what your audio sounds like, load up Listen Live on the website, pick up your radio, give your call sign, and say this is an audio test. No response necessary. Then wait a minute and listen to the playback. Still stumped? Come into our Zoom room for advice at bit.ly/ECR Daily. The ECR Helpline. If you're having a difficult time connecting to the ECR or need to make us aware of a problem, call or text our helpline at 746-427-4142. We'll help you the best we can. This is not for bad audio or rude hams. This is for things that need current attention, like someone sleeping on the mic about to time out the system, or someone being very aggressive. We appreciate your help. Did you know that we have a gift shop? You can help to support the East Coast Reflector at the gift shop. You can get your call sign put on an ECR shirt starting at $17.68, coffee mug from $12.60, or a polo from $22.49. Be a contributor. Do you want to help contribute to the magazine? Send in your article, project, story, comment, and suggestions to editorecr@gmail.com. You don't have to be a good writer if you have a good story. Everything will be polished and sent to you before it's published. You should know. The East Coast Reflector and its Reflector Magazine is all volunteer run. We charge nothing to use the system and nothing to subscribe to the magazine. The system has hundreds of nodes and repeaters connected at any given time. We incur a lot of expenses to maintain such a large system. If you use the system or enjoy the magazine, please consider helping by contributing to the system by going to eastcoastreflector.com and click on Donate. Your contribution is greatly appreciated.
The Basics. Frequencies versus Bands. By Vicky KE8VKY. In amateur radio, frequency is the exact number of times a radio wave oscillates per second measured in Hertz Hz. For example, a signal at 7.15 MHz oscillates 7,150,000 times per second. Frequency tells you precisely where your signal sits on the radio spectrum and affects how your signal travels. A band, on the other hand, is a range of frequencies grouped together. For instance, the 40-meter band covers roughly 7.000 to 7.3 MHz. Bands are assigned by regulators like the FCC, and each band has typical uses, propagation characteristics, and licensing rules. Some bands are better for long-distance communication, while others work best for local contacts. You can think of it like this: a frequency is a single radio channel, while a band is the whole street of channels. Knowing the difference helps amateur radio operators choose the right spot to operate, select the best antenna, and predict how far their signal will travel. Popular amateur radio bands with frequency ranges. Net questions. Here's a list of most of our net questions. Ever wonder how your answer compares or what the results were? Click the question to see the results. There's questions from the Morning Brew, and the TechNet and the TriviaNet. The ECR has unique log sheets and you're welcome to watch along. You can see where you are on the log, answers to the questions, and even birthdays and more. Go to ecr.radio/logs to get access to view all of the net logs. Text or email to get your spot in the log. Our nets can be so busy that people have a difficult time getting in. We want to help everyone get on the air, so we came up with a unique way to get more people on the air. Text your call sign to 716-317-9050. Standard messaging rates apply. You can also email your call sign to text@ecr.radio. This will get you onto the log. This is not for ins and outs. It's to help get people on the air and through the pileups. Our nets.
Celebrity Call Sign by Joe, KB2TFB. Joe was born on March 29, 1941, in Philadelphia, Pennsylvania, the second son of Joseph Sylvia. When he was 7, he moved back to the family farm in Cinnaminson Township, New Jersey. His immediate family has 3 children. Like the farm's peaches and tomatoes, the family grew and ripened in a healthy and carefree environment on the eastern bank of the Delaware River. Among Joe's fondest boyhood memories are collecting stone arrowheads left on that land by its much earlier inhabitants, and erecting, together with his brother Hal, numerous large, rotating, ham radio antennas high above the roof of the 3-story Victorian farmhouse. With one such project they managed to shear off the brick chimney, flush with the roof, much to the consternation of their parents. That incident was one of many practical lessons of his youth, not all absorbed in the most timely fashion, involving ill-advised shortcuts towards some goal. Joe was educated mostly at Quaker institutions, in particular Moorestown Friends School and Haverford College. In school, mathematics was his first academic love. Somewhat backward high school introductions to chemistry and physics did not dampen any enthusiasm for science. They just gave him more time for sports, than a greater passion. Soccer, basketball, baseball, golf, and tennis claimed much of his energy through the Haverford years. Concurrently, though, Joe began discovering the delights of what science is really about. A fascinating senior honors project in physics allowed him to combine a working knowledge of radio frequency electronics with an awakening appreciation of scientific inquiry, and to build a working radio telescope. His principal references were an old friend, the Radio Amateur's Handbook, and an early book on radio astronomy by Posse and Bracewell. This thoroughly enjoyable honors project cannot really qualify as research. Everything accomplished had been done by others years before, but it provided excellent lessons in problem solving of various kinds. It also delivered a valid reason for selecting something Joe had been hoping to find, a desirable field of physics in which to pursue graduate studies. Our celebrity is well known in the field of astronomy for discovering binary pulsars, and in the field of amateur radio weak signal communication, and has the call sign K1JT. He had previously held the call signs K2IDP, WA1LXQ, W1HFV, and VK2BJX when in Australia. Dr. Joe Taylor has been active in developing several computer programs and communications protocols, including Whisper and WSJT, which stands for Weak Signals/Joe Taylor. Previous celebrity call sign articles. QCell cards of K1JD, Dr. Joe Taylor. Courtesy of hamgallery.com. This month's user-submitted pictures are from Facebook submissions.
Radio Questions Answered by A.P. Peck, The Experimenters, Library No. 3, 3D reprint, February 1924. For entertainment purposes only. Use common sense. This is from 1924 and outdated. The original article is very long. Parts of the article will be split up into 7 pieces over the next issues. The full original article can be found at World Radio History. Come in The Experimenters, Library No. 3, Part 3 of 6. How does this apparatus work? Continued Question number 19. What is a variometer and how it is used? Answer. A variometer consists of two coils of wire wound on insulating tubes and arranged one within the other. The center coil is arranged so that it can be rotated within the other. Their windings are connected in series with one another. When the coils are parallel with each other and the windings running in the same direction, the entire instrument has its greatest inductive value and will tune to the highest possible wavelength with the particular size of coils used. Now, however, when the coils are rotated through 180 degrees and the windings are running in opposite directions, they are said to be bucking each other, and their inductive value is at its lowest point. Therefore, the wavelength is at its lowest point. A circuit diagram is given with this answer, which shows a variometer connected with a crystal detector. This is probably one of the simplest forms of radio receiving sets, but will not give very sharp tuning. Question number 20. What is a variocoupler? How does it differ from a variometer, and how is it used? Answer. A variocoupler may have practically the same external appearance as a variometer, but the two coils are not electrically connected together. The outside or stationary coil is usually tapped, so that various numbers of turns of wire may be used as desired. These taps are usually brought out to switch points, so that correct adjustment may be obtained. The inside or rotor coil is not tapped in any way, but a current is induced into it by the stator or outside coil when current is flowing through the latter. A circuit showing a variocoupler connected with a crystal detector is shown in the accompanying diagram. The greatest difference between a variometer and a variocoupler is that in the latter there is no electrical connection between the two coils. A variometer and variocoupler may be used interchangeably in practically all cases, but the variocoupler will give much greater selectivity in tuning. That is, it will allow the operator to eliminate one station and listen to another when both are transmitting on practically the same wavelengths. After years of experiment, these two instruments have been assigned to their various uses in radio, several examples of which will be found in the diagrams throughout this book. Question number 21. Shall I use a loose coupler or a variocoupler for receiving? Answer. In theory, there is no difference between the use of a loose coupler and a variocoupler, but in actual practice a variocoupler is usually found to be the handiest form. This is for the simple reason that it can be readily mounted on a panel and the controls so arranged that they are accessible and instantly adjusted. A loose coupler will always give excellent results. In fact, exactly the same results as a variocoupler, but it is not practical for panel mounting, an obvious disadvantage in the type of sets most generally in use today. Question number 22. What is a vernier? Answer. A vernier is any device which allows very close or accurate adjustment of any particular instrument. This is its meaning as applied in radio work. Verniers are usually used on variable condensers only, but in some cases they are used on rheostats, as will be described later. As will be seen, there are illustrated 3 separate and distinct types of verniers for use on condensers. One type is designed to be placed on the outside of a panel and has a rubber ring which engages frictionally with the condenser dial. By turning the small knob to which the rubber ring is attached, very critical adjustment can be obtained as there is a greater reduction in the ratio of speed between the rubber ring and the edge of the dial than could be accomplished by turning the dial alone. Sometimes it is desirable to use a second variable condenser placed in parallel with the main condenser, the former usually having a very small capacity. This small condenser is then known as the vernier. One of these types is illustrated and usually consists of 2 or 3 plates. Since the total capacity of this vernier condenser is so very small, even a great degree of rotation of a single movable plate will give only a very slight variation in capacity. The third type shown makes use of a separate plate, which is built as part of the condenser itself. The single rotary plate is turned by means of a knob on the side of the dial, which passes through to the outside of the panel, where it can be easily operated. In another type shown, the vernier or single plate is operated by means of a small knob in the center of the larger one, which rotates the plates of the main condenser. One of these attachments is quite necessary in radio reception in order to be able to tune in a certain station sharply without having any interference from other sections which happen to be transmitting at the same time. Question number 23. What is a rheostat and a potentiometer? Answer. Due to the way in which vacuum tubes are constructed, it is necessary that only a certain voltage be supplied to the filament. In order to regulate the voltage delivered by the batteries, it is necessary to have some sort of a resistance in the circuit. By resistance is meant some hindrance to the electric potential, or voltage which does not allow it to force through as many amperes as it is capable of doing. In effect, it is the same as using a small pipe to transmit water rather than a large pipe. The larger pipe will allow more water to flow through it than a smaller pipe at the same pressure. The smaller pipe may be thought of as having the most resistance. The resistance required in the filament circuit is supplied by the instrument known as the rheostat. 3 types are shown in the illustrations. One type makes use of carbon discs which are compressed or released in order to vary the electrical resistance, and another consists of many convolutions of wire wound on a fiber or composition strip, which is then bent in the form of a circle. A switch arm is so arranged as to make contact with successive turns, which process varies the amount of wire placed in the circuit. With detector tubes, it is practically essential to have minute regulation of the filament voltage. Such regulation is afforded by a vernier rheostat such as illustrated. In this case, an arm is revolved around the base of the rheostat, which makes contact with a single turn of wire set in a groove around the edge of the base. Very close regulation of the amount of resistance in the circuit can be obtained with this type of rheostat. Also, when the carbon pile rheostat as aforementioned is used, very close adjustment is possible as the resistance does not vary greatly when the pressure is increased slightly. Thus, the effect makes the rheostat a vernier. A potentiometer has somewhat the general appearance of a rheostat, but is supplied with a connection to each end of the wire wound thereon, as well as one to the switch arm. The resistance of potentiometers in use today is usually between 200 and 400 ohms, the ohm being the unit of electrical resistance. To be exact, the ohm is the amount of electrical resistance through which 1 volt will force 1 ampere of current. A potentiometer is usually used in various circuits in order to supply a certain voltage to different instruments. It is particularly useful in radio frequency circuits, as shown in the diagrams in this book. Question number 24. What is a grid leak? Answer. A grid leak is a very high resistance, usually having a value of from 500,000 to 3 million ohms, which terms are expressed as 1/2 megohm to 3 megohms. It is connected either across the grid condenser or from the grid to the filament of a vacuum tube. Continues in volume 26 with why are an aerial and ground used? Ask an Elmer Zoom meeting. Everyone is welcome to come in and ask questions or help answer questions. The first and third Thursday of each month. On the second Thursday of each month is our ECR virtual town hall meeting. Stop by to ask questions, make suggestions, and learn about the system. Operator oddities. A new owner took over a local AM broadcast radio station. All sorts of complaints came into City Hall. I was picked to head the committee. The best complaint was from an elderly woman who said she could hear music and talking from her refrigerator. The poor woman wore a hearing aid. But she was positive she heard it while in the kitchen, putting up preserves. The station did have a problem in their antenna system, though. Multiple complaints about it were received. They did resolve it. Rich. Submit your stories to editor@ecr@gmail.com. Radio crossword. All of the answers can be found in this issue of the magazine. Ham comics. Strong signal, weak domestic approval. Try a quick little general exam practice. A handful of questions to keep your skills sharp or to help practice to take the test. Birthday call sign word search puzzle. You can add your birthday by going to ecr.radio/birthday. And of course, a jigsaw puzzle. You choose the number of pieces and put it together from your device.
Continued from page 34. Horizontal. The horizontal dipole, 1/2 wavelength, antenna is physically mounted on a pole or mast. This means that the maximum radiation field is about 7 meters, in my case above ground. The benefit is that I can see about 10 dB more signal in tests in my back garden using a horizontal dipole. If there are no obstructions, then the difference between vertical and horizontal is almost nothing. The width needed for any frequency is given by the formula. Length is 142.5, divided by frequency in megahertz. Dipole antenna clearing obstructions. Trees have lesser absorption on horizontally polarized antennas. Portable operation. When I operate a portable station from Rosersberg, outside my place of work, I use an MFJ 1979 16.5-foot stainless telescopic antenna. I have also added a coil of 4 mm diameter aluminum wire, base loading coil to make the antenna electrically longer. The coil is 53 turns, 10 centimeters diameter wound around a tin of pineapple and with 1 centimeter turn spacing. I also use 10 millimeters diameter plastic tube to support the coil, with 5 millimeters holes drilled at 1 centimeter intervals. 3D printed top and bottom spacers secure the coil around the antenna. MFJ 1979 telescopic whip 16.5 foot, 5.03 m, with tappable base loading coil. I connect the feeder shield to the ground radials and the center conductor to a taping of the coil with an alligator clip. With this arrangement, and I can get about 1.1 to 1 on 3.5 MHz through to 10.1 MHz with the full 5.03 m telescopic antenna. Be aware that the screw bolt head at the bottom for mounting is not metric. If you have a wooden packing crate, then you can make holes in the top and bottom to support the antenna. I use this as a vertical ground plane antenna with 3 5.4 m radials. The telescopic antenna can be physically extended or retracted to get resonance at any frequency between 14 and 29.7 MHz. VisWAR equals 1 to 1 on all bands. My antenna supported in its wooden box, ready for portable operation. So my portable antenna needs no guy ropes and covers 3.5 MHz to 29.7 MHz without any antenna tuning unit at all. No unbalanced feeder. With only 50 watts I can still put out a very respectable signal and the whole lot, antenna, radio, car battery and cables, fit in the trunk of my little car where the spare tire used to be stored. The bad news is that measurements show something like a 10 dB loss of received signal when I use this antenna in my garden at home. I even tried to use thicker aluminum tubes, but the results were exactly the same. I really need to go horizontal. Coils for permanent use. If you are fortunate enough to have some land without nearby obstructions, then the vertical ground plane antenna can give good results. 5.2 meters is perfect for 14 MHz, but you can also use it for lower frequency bands by adding some inductance. You can use my tapping method for portable use, but for permanent installation you can fit a base loading coil. If the antenna is too short, then it will cave capacitive reactance. You can calculate and win coils to do the job, which you can switch remotely using a latching relay. Energized with DC from your radio room, you can use the RF coaxial cable to pass the DC to the latching relays, using the polarity and diodes to select which relay you want to energize. My coils wound on 20 millimeters diameter, plastic tube. The formula was published in QSD, September 1974, for calculating the capacitive reactance and the inductor value to cancel it. I have changed values to decimal and simplified the formula, so only coils at the low impedance feed point are considered, no offset. Here is a calculator for my modified formula. Formula originally published in QSD September 1974, where L microhenries equals inductance required for resonance, Ln equals natural log, F equals frequency megahertz, A equals overall antenna length feet, B equals distance from center to each loading coil inches, D equals diameter of radiator inches. If you want an accurate online form in feet and inches, then a good resource is M0UKD's homepage. Calculator for base loading coil inductance. A negative value means the wire is longer than 1/4 wavelength. Now all you need to do is take the number of microhenries and put the value in the coil winding formula to find out the number of turns. Just guesstimate the coil length, say 100 millimeters, and see how many turns you need. Multiply this by the diameter of the wire you are using. I use 0.8 millimeters diameter, and re-enter this in the formula. Repeat a couple of times until the result is the same as the last result. Calculator for single-layer coil. The dipole horizontal antenna. The dipole is a half-wavelength antenna, so a 7 MHz antenna must be 142.5/frequency, MHz, long, equals 20.3 meters long, fed in the center. That will not fit in my 8M wide garden. The 14.175 MHz center of band dipole will be 10.053 meters. I can slope the antenna to make an inverted V, and also place it a little diagonally. That way the antenna only needs 9 meters of garden space. Another interesting point is that the antenna has about 70 ohms-ish at resonance, although this can vary greatly with proximity of other antennas, and even the ground. This is at the dipole center feed point. If not resonant, then the impedance is much higher. So 2 or more antennas can be connected in parallel to form a dual or multi-band dipole. This is what I did with all the horizontal experiments. Base loading a dipole. Base loading a dipole requires 2 coils to be fitted, located at the feed point. These are the same coils and calculations as used for the ground plane. It is not possible to use my tap coil unless you want to lower the antenna every time you want to make an adjustment. So you do need fixed coils. You can trim the antenna lengths to get the frequencies perfect. Base loading coils fitted to a dipole. Dipole antennas can be connected in parallel, so all I need to do is to calculate the required length of each dipole, then cut the wires to the correct length. With my 9 meters of space, I can have a maximum of 10 meters, so I can have a full 1/2 wavelength for all bands from 14 MHz through to 29.700 MHz. No problem. Multiband base-loaded dipole. I use the formula 75/frequency megahertz for each 1/4 wavelength section, that is to say, without the 5% reduction due to end effect. This means they will all be a tad too long, so I can always shorten them a little to tune them exactly. So here are my antenna length, with a few cm spare for trimming. Base-loaded performance. This proved to be a bit of a problem. I found that when base-loading coils are used, the Q factor increases, bandwidth is more narrow, and the efficiency falls because there is less metal in the air. The greater is the coil to wire length ratio, so the greater is the problem. Everything works okay. It looks a bit Heath Robinson and makeshift, but it is the technique and performance I was testing. Also, I am not at home in daylight, so please excuse the night photographs. First 5-band experiment, temporary makeshift assembly. This first experiment works well and achieves all operational goals. It uses loaded dipoles for 3.7 MHz and 7.1 MHz, but straight no coils for 14.17 MHz, 27.3 MHz, and 29 MHz. All 5 dipoles are connected to the same feed point. A couple of extra loose spaces were added in case I wanted to add more dipoles for 18.1 MHz and 21.2 MHz. Conclusion: coils do get you on the air and are simple to construct. I clearly needed to get a bit more metal in the air and to eliminate the coils if I want to cover the full band and have a better efficiency below 14 MHz. Another method is folding the dipoles. Experiment number 3, final version. Folded linear loaded dipoles. There are a lot of designs for linear loaded dipoles. All you need to do is Google them. So I did a lot of reading and decided to give it a go. The results were quite surprising. For 7.1 MHz, I needed each 1/4 wavelength section to be a tad longer than 10 meters. So I used my 5 meter plus 5 meter dipole, working on 14 MHz upwards, and added more elements. Each 1/4 wave element must be a bit over 5 meter, so I made a zigzag formation of 5 meters long, doubled back for 2.5 meters, then doubled back once more for the other 2.5 meters. This gives 10 meters of wire in each 1/4 wavelength element, but I could not find the resonance. Folded linear loaded dipole with the extra 3M extension wire. Wherever it was nowhere near 7 MHz, and I could not find it with my radio. So I used a signal generator, impedance bridge, and a 100 MHz oscilloscope. I found a beautiful dip in the impedance at about 9.4 MHz. This means that the effective length was 7.5 meters. In other words, the 2.5 meter folded back section cancels out 2.5 meters of the total length. Removing my socks and counting on my fingers and toes, I reckoned that I needed to add another 3 meters to each half. I didn't have enough space in the garden, so I scratched my head a few times and realized that the center of my dipole is 7.5 meters above the ground, but the ends are 3.5 meters above the ground. So I added 3 meters to each end and just let the wires hang vertically downwards. Bingo! It now resonates at 7.120 megahertz, and it still fits in my garden, but only just. Checking the bandwidth, I find that it covers the whole 7 MHz band with a visual of less than 1.4 to 1 from 7 to 7.2 MHz. The voice of Russia is romping in, large as life and twice as beautiful. The only slight observation is that as the wind blows, the dangling 3-meter ends move around and the VSWR varies very slightly. A bit of nylon fishing line tied to a rock stopped that. Assembly and trimming. Assembly is easy. All my dipole elements were deliberately cut too long. I don't want copper wires exposed, so joints are not acceptable. Instead of cutting, I rolled up the wire ends to shorten them. It was a little pain in the rectum to feed the 3 mm wires through the holes, but the effect is that they are really secure and do not shift easily. I also secured the wires using 0.8 mm magnet wire. Method of rolling back. 10 centimeters rollback equals 10 centimeters electrical reduction. Method of securing the wires using 0.8 mm diameter enameled copper. If I need to shorten a dipole element beyond the support/spacer tubes, then the surplus wire can also be doubled back and twisted around the element wire to cancel some of the unwanted length. For example, if you have 5.2 meters and you want 5.0 meters, then you only need to fold the last 100 millimeters back up the dipole wire. It will be 5.1 meters, but electrically 5.0 meters. Method of folding back. 10 centimeters fold back equals 20 centimeters electrical reduction. I used plastic 30 centimeters electrical conduit tubes, 1 centimeter diameter for the spacers, except the end spacers. These are 2 centimeters diameter, since they need to be stronger. I used cable that is 3 millimeters diameter, including the insulation, so all spacers are drilled with 3 millimeters holes with 46.66 millimeter separation, starting 10 millimeters from each end. Here are the dimensions of the antenna as calculated before trimming, 1/1/2 shown. Water at the feed point can have an impact on a multiband dipole, so I sprayed that part of the installation with a water repellent spray intended for waterproofing clothes and shoes. This means it is a lot more stable in all weathers. Water also freezes in Swedish winters, and you can get a lot of ice building up. Completed antenna. Final version. Quickly painted black. Visual profile. This was one of the major aspects for me. If it looks makeshift and is an eyesore, then it can attract unwanted attention from the community guys. Original experiments were done with a 5.5 meter mast, my original ground plane antenna, and it was so obvious, with shiny metal, that it stuck out like a sore thumb. Now I have used 38 millimeters diameter steel TV mast tubes and raised it to 7.5 meters. I painted the mast black, and it is a lot less obvious from a distance. Nothing to glint in the sun. The original plastic spacers for the elements were all spaced 650 millimeters wide, white plastic. The new ones are all 300 millimeters long plastic tubes, painted black, 20 millimeters diameter tubes for the end and center spaces. All the middle tubes are only 10 millimeters diameter. I also sprayed the wires black. The guy ropes I also boiled on the stove in black clothing dye. The dye did not take too well because the flagpole line is made of nylon, but they are dark enough to make them less visible. The mast guy ropes are also fitted to the center of the mast, not the top. In this way, the mast pole is still rigid and not visible over the surrounding bushes. Another point is that the final version is so weighted that the 6 band elements are rotated horizontally along the axis of the dipole, instead of vertically. When viewed from the side, all the elements are in the same plane, so you can only see one element. You have to stand beneath the antenna array to see all 6 elements. With all of this, the community guys will hopefully have very little to see. Conclusion. This weekend I was on the radio and using all 6 bands. 10M and 11M are almost dead, but I had some good contacts on 21 MHz, 18 MHz, 14 MHz, and 7 MHz. I tested the 24.9 MHz dipole, but that band is very narrow, so I have removed it. My antenna does not need any ATU. I don't believe in them. And the test broadcast stations show that the antenna is performing as well as I can get it, given the restricted space available. It is difficult to see the antenna unless you are specifically looking for it. Not even guy ropes are particularly visible. The guy ropes are secured to my 2-meter-high fence on the one side, and the neighbor's fence at the other side. The neighbor is a wonderful woman, and we have helped her a lot with things, like repairing the kitchen lamp and taking garbage to the city dump. She was more than willing to allow me to tether my rope to her high fence. One of the guy ropes also supports the RG58 feeder cable, so anyone wandering into our garden will not get strangled with hanging wires. One last point is that I did some tests with the 1:1 feeder balun. At 50 watts the VSWR was perfect, but when I increased the RF power to 150 watts there was some movement on the VSWR meter. I replaced the balun for one that is ventilated, covers 1.8 MHz to 30 MHz, and can stand up to 1 kW. Future project. Yes, I do have plans for the future. One of the ideas I was given from the forum was a mechanical arrangement to make the dipole lengths variable. I think that was a really smart idea, but with a little thought I can make a variable length dipole without any sliding contacts. Another idea is to see if I can use some invisible magnet wire in the community tree that is beside my garden. I had to covertly trim parts of the tree to prevent branches from getting tangles in my dipole antenna. The tree also serves to hide my antenna a little, but my thought now is that perhaps I can use it in some other way. I also want to do something about all the QRM that is blanketing the 3.5 MHz band. Perhaps I can add another element to the dipole for good transmissions, but use a separate antenna for receiving? Loops and frames are good, but for reception it is the signal-to-noise ratio that is important, not the signal level. Finally, I have had a lot of fun experimenting and building this project. At long last, I have managed to get a usable antenna system for the coming years. I hope that some of my thoughts and experiments can help you to become operational if you also have a small garden with a limited space. As I have learned, nothing is impossible if you can be a little inventive. If you have any comments, suggestions, or ideas for improvements, then please do get in touch. I would prefer contact via my forum as I try to avoid email as much as possible. The SM0VPO forum is here. Very best regards from Harry Lythal, SM0VPO Marsta, Sweden, QRA equals JO89W. Previous articles by Harry SM0VPO.
Silent keys. Please keep these people in your prayers and their families to give them the strength, encouragement, comfort, and peace of mind and heart they need. KB5VDB Ronald, NC4AT John, KC3TDR Frank, KC3FMJ Brandy, AE2EE Dennis, KD2BRN Charles, KZ1B Robert. Disclaimer. The content, opinions, and views expressed in this magazine are those of the authors and contributors and do not necessarily reflect the opinions or views of the publisher, editorial team, or affiliated organizations, or anyone else. All articles, images, and information provided are for informational and entertainment purposes only and should not be considered as professional advice. The publisher, ECR, and its volunteers assume no responsibility for errors or omissions in the content provided. Readers are encouraged to verify all information independently. The use of trademarks, logos, and brand names does not imply endorsement. Reproduction or redistribution of any content in this magazine, in whole or in part, without prior written consent from the publisher, is strictly prohibited. For inquiries or permissions, please contact Vicky KE8VKY at KE8VKY@gmail.com.